It's my great honor to introduce my friend and also my colleague from University of Tianjin University. And it's my great honor to introduce him to give us a lecture. Dr. Zhongxing Wang is a distinguished research professor at the School of Civil Engineering at Tianjin University. And he leads a research group. I think that we had a conversation yesterday. And it's a very large research group, comprised over 20 research students. It's a big group, and his primary research interest in aluminium alloy structures, with a special emphasis on fire behavior, aluminium alloy timber structures, composite structures, and also mechanical properties and structure properties, behavior of metal 3D printed structures. So he has led multiple structure projects from the national funding institution, and he has published over 60, 70 high impact journal papers, and has been awarded 15 domestic and international invention patents. So, and also serve as a editor of CECS, it's the China Association for Engineering Construction Standardization. And his research outcome has been implemented in many projects. So with no further introduction, I wanted to leave the platform to Dr. Wang. Thank you for coming, for giving us a lecture. The platform is yours.
Okay, thank you. Thank you for the introduction. Xiang is my colleague during my visiting study in Imperial College, and our collaboration has been over 7 years.
Yeah, I think more than 7 years.
Yeah, and also thank you so much for the students in the room and the professors and the students online. The title of my report is Local Buckling Behavior and Design of Aluminum Alloy Cross Sections at Elevated Temperatures. And I will introduce from the 6 aspects. First, the background. As we know, metal structures are popular recent years. Among them, there is a special kind of metal structure, that is aluminum alloy structure. Because of its merits, such as high stress to weight ratio, good corrosion resistance, the ease of process, and aesthetically pleasing, and also high recyclability. The application of aluminum alloy is developing more and more fast. But although there are several merits of it, some characteristic of aluminum alloy we should pay attention to in the real engineering practice. For example, the elastic modulus of aluminum alloy is very low relative to steel. It is around 1/3 of steel. So the buckling performance of aluminum alloy members is not as good as steel members. More than this, the elevated temperature performance of aluminum alloy structure is also not as good as steel structures. First, it will melt at around 600 centigrade. And it has a sharp reduction in elastic modulus and yield stress when the temperature is higher than 300 centigrade. The pictures in the right-hand side present the characteristic of this. So, in order to accurately design the high temperature behavior of aluminum alloy, current codes such as Eurocode, American code, and Chinese code give a lot of design formula, but there are some limitations of them. The first one, although in high temperature, aluminum alloy degrades but the codified methods neglect it. The second point is that current codified methods neglect the shape variation of the constitutive curves of aluminum alloy. There is a stronger strain hardening behavior at higher temperatures, and this point influence the high temperature behavior. So the codified method should consider this. So this is the background. To overcome the current limitation, we carry out a series of studies during the past 5 to 6 years. The first is at the material level. We carry out for two kinds of material. The first one is the high stress aluminum alloy. It is 7,000 series. And the second one is normal stress. It is 6,000 series. And in total, were tested during the in the range of ambient 400 centigrade, and these kind of tests were carried out in two conditions. The first one is state. The second one is the post-fire state. And for the post-fire cases, there are two kinds of cooling method, air and water. So we got the stress strain curves of all of the specimens. It is steady state tests under high temperatures. The stress degrades clearly when the temperature increase. But for the post-fire tests, the data scatter much more notably than the steady state tests. And these are the failure modes. And we can see that for the steady state test, when the temperature rises, the ductility became the deformation capacity became better. Yeah. But for the post-fire tests, the deformation capacity remains almost the same. Based on the material test results, as well as the results collected from literature, we proposed a two-stage constitutive model. Actually, this model is for the high temperature test, high temperature material property, and it is based on ambient temperature constitutive model of the two-stage one, proposed by Xiang and me, and published in Journal of Structural Engineering in 2021. And it is really a highly cited paper. Till now, I think the citation of it is around 150. And this one, because we can see that there is a very important point. It's called the middle point between the yield point and the peak point. Why we use this point to capture the second stage? Because for aluminum alloy, sometimes it will fracture before the strain equals to 1%. before 1%. But other constitutive model of the two stage, for example, some stainless steel constitutive model, it adopts epsilon 1 for the second stage. But for aluminum alloy, we cannot use this point because it may fail before that point. So we propose the middle point between the yield and the peak point. And finally, we calibrate the model from the test results and found that the model is rather accurate. And we validate the model through the experimentally obtained data. So based on the material level investigations, we start to investigate at the plate level, because all the cross sections are composed of plate elements. So the plate level research should be the first step. So we carry out numerical research based on over 1,000 models. So this is the model assumption. And first, we should validate the plate FE model. We use published result from Netherlands. I think it's a Netherlands researcher, and found that our FE model is very accurate. And then we can use this FE model to carry out parametric analysis. And the first step, we use the more than 1,000 data to evaluate the accuracy of existing models. The first one, the European standard. We found that because of the different degradation rates of elastic modulus and yield stress, the accuracy of the Eurocode method is not good. It's over conservatism. And then we evaluate the Chinese standard, because the Chinese standard is very similar to European one. So the outcome, the results is also similar. And then we assess the American standard. We found that although the accuracy is better, but it's excessive scattered. After the assessment of the codified methods, we also evaluate the methods proposed by other scholars. The first one is the Majors. It's the co-author that carry out the tests that we use to validate our FE model. And we can see that his method is much more accurate, but some data is overestimation at high temperatures. To make it, we can see the data here, with the dark color. It means the very high temperature. For this data, the design method is dangerous. So we found that the existing method is not accurate and very scattered. So it's essential to propose a new model for the plate buckling resistance. So we proposed new equations based on the European code system. And for our formula, we incorporate two new parameter, which is lambda p theta and gamma theta. The first one accounts for different degradation rates of E and Fy, and the second one captures the stress strain curve variation of aluminum alloys. And finally, we use the test data as well as the FE data to validate the proposed method. We can find that the accuracy and the consistency are both good. Yeah, this one is for the outside element. This one is for the internal element. And finally, we compare our method with the existing methods, and it exhibits around 15% higher accuracy compared with Eurocode method. So this level is the plate level. And the cross-section is composed of plates, but there is a new problem. That is that the element interaction. So in the fourth aspect of my report, I will introduce how we dealt with the plate element interaction. Before that, before the theoretical work, we also carried out a series of cross-section tests. So the tests include three kinds of cross-section types. They are RHS, SHS, and H section. All of them are in class 4, that is slender cross-section. And the material we employed was high-stress aluminum alloy, and the temperature range from 20 to 400 centigrades. And they are all steady-state tests. Actually, we designed an electric heating high precision furnace by ourselves, and this furnace actually is very useful and convenient for us. And the test was conducted in Tianjin University. Before the test, we scanned the imperfection of all of the specimens by scanner. And then we process the data through the software of geometric wrap. And we found that the high-stress aluminum alloy cross-sections exhibits smaller initial geometric imperfections compared to the normal stress cross-sections due to its strength advantage. During the transportation and fabrication, the high stress make it less possibility to deform, so with lower imperfection. And this is our temperature time curve. It presents that the test is under high precision temperature control. I think for the students or professors who carried out high temperature tests, he will know it's rather difficult to get such a temperature curve. And these are the failure modes. Some of the specimen failed in yielding, that is stress failure, because of temperature increase. Because with the rise of temperature, some local buckling will shift to stress failure because of the different degradation rates of E and Fy. So this highlights the necessity for our investigation and new design methods. And for each section, all of the specimen failed in local buckling. The deformation performance increases significantly with rising temperature, and the local bubbling becomes more pronounced at high temperatures. And these are the load displacement curves. And after tests, we developed FE model and validated the models. And these are the validation of the load displacement curves. And we got a very high accuracy of the FE prediction. And then we used the FE model to carry out a parametric study. The number of the models are around 700. So till now, all of the test data and FE data we have got. Now we will use all of the data to develop a new method to account for the interplate interaction. And this is very new and very important for the cross-section design, because in the design of all the metal structural cross-sections, all of the codified method till now in the history did not consider the plate interaction because it's rather difficult. And some scholars have accounted for this. I just introduced two methods. One is proposed by Professor Gardner. It is an equation to account for this, but this equation is not very accurate. It has some errors. The second one is proposed by Ben Schaefer. And this method is a numerical method that is CUFSM. Although it is very accurate, but for designers in a company, I think he cannot use this to design a cross-section. So to overcome this problem, we develop a new method using machine learning. I think machine learning also is also a numerical method, but it's very easy to use for designer, and it is also very accurate, much more accurate than any design formula. To develop an accurate machine learning model, we select a series of the candidate models, and among them, we find that the support vector regression SVR model is the best one. So, in the following prediction, we use this model. We adopt this model, and finally, we propose a cross-section level method based on two parts. The first part is our proposed plate method I just introduced in the third chapter. And the second part is our machine learning based predictor for the plate interaction. That is based on sigma CR theta. CS means the cross-section. So we compose these two parts into our new method for cross-sections. So this is our new method. So what's the outcome? What's the advantage of our new method? We can see that we evaluate all of the cross-section level method again. Cross-section level of the European standard and Chinese standard. Now we can see the error is very large. And also we can see the method from American standard and also the continuous stress method proposed by Professor Gardner. For CSM, although it is accurate, but the scatter is also large. And finally, these are the outcome or results of our proposed method. We can see that our method has superior accuracy, around 15% higher than Eurocode, and minimal data scatter. So this is our way to design the aluminum alloy cross sections under elevated temperature. And after the design method investigation of the cross sections at steady state conditions, we also did some research on the transient state capacity of the cross section and the fair protection method. So in this part, we carried out tests on the CHS circular hollow section, and the material is a normal stress aluminum alloy. And the transient state loading with the heating rate of 15 centigrade per minute. And then I want to introduce some interesting thing. Actually, I am in the area of structural engineering, but we developed a specially designed coating for aluminum alloy with an institution in Sichuan province, China. And this kind of coating is very special because the chemical composition of it makes it has a lower intumescence onset temperature, because we commonly use the steel structure coating for aluminum structure, but this kind of intumescence start to work at a very high temperature, but at that temperature, aluminum alloy start to fail, start to lose its strength. So we need a new intumescent coating with a lower onset temperature. This is the first one. The second one is that the ordinary coating for steel structure, it is corrosive, but the new one is non-corrosive. So we call the new one as type A and the ordinary one as type B. And we use these two kinds of coatings on our cross sections, stub column members, and then we put them into furnace to see what's the difference of these two coating. These are the test setup, and these are the temperature measurements and the temperature time curves. And first, we found from the temperature time curves of the two coating protected members that type A outperforms type B in thermal shielding and fair endurance. And then from the failure modes, it's more evident. First, let's see the ambient temperature test. It occurs elephant foot local buckling at the column ends. I think this is very common. But for the elevated temperature test, it's rather different, because our furnace, the temperature in the middle is higher than temperature at both ends. So the buckling point shifts to the middle. And the most interesting thing is the coating protected structure. So for this one, this is protected by our newly developed coating. We found that the coating is maintained integrity. But for the members protected by the steel structure coating, it was spouting from the specimen because of its poor adhesion. And these are the displacement temperature curves and the critical temperature stress ratio curves. We found that the displacement temperature curve exhibits a distinct three-stage regime, including expansion, compression, and failure. And the higher stress ratio significantly degrades the TCR, that is the critical temperature. Okay, based on the material level investigation, plate level, cross-section level, and the fair protection investigations, we got mainly three conclusions. The first is the limitation of our existing design methods. The first one, for Euro code and Chinese code, it is overly conservative. For American code, it is significant scatter. And existing methods from other researchers, they are accurate but scattered and not sufficiently reliable. And we reviewed the local buckling behavior from our series of tests and numerical studies, including three. The first one is the slower degradation of E compared to Fy delays the buckling at elevated temperature. I think this is a new finding based on our research. The second one is the shape variation of the constitutive curve accelerates the buckling. They are opposite, but the first one is dominant. The third conclusion is that we propose the design method of the cross-section based on our investigations. It is with high precision and with the consideration of the characteristics of aluminum alloy at elevated temperature. And our proposed design method was verified against experimental as well as numerical data. And we have published around 8 papers, and among them, one is under review now. Okay, thanks again for giving this lecture to the researchers from University of Bristol. And if possible, I warmly welcome you to visit Tianjin University. And I also introduce my master student, Yu Hang. Actually, is my master student around 2 years ago. Yeah, he graduated from Tianjin University and then come to University of Bristol to pursue PhD under the supervision of Professor Xiang Yun. And if you want to go to Tianjin University to visit Tianjin, please tell Yu Hang, and he will tell me. Okay, thank you again.